Now, let's use this example to illustrate the difference between sampling with replacement and sampling without replacement in calculations of probabilities. We'll have a bag that contains 10 balls, 5 red, 3 blue, and 2 white. In the first instance, if you sample with replacement and your first 2 drawers are both red, what is the probability that the third drawer is a blue? Now, since you replace the first 2 balls back into the bag, so when you go back to draw the third ball, there are still 10 balls in the bag at the same composition, 5 red, 3 blue, and 2 white. Therefore, the probability of drawing a blue ball is, at the bottom is 10. Why? You have 10 possible outcomes. You have 10 balls in the bag. On the top is 3. You have 3 different ways to obtain a blue ball. 3 over 10, 30%. Now look at this. If you sample without replacement and your first 2 selections are both red, what is the probability that the third drawer is a blue? Since you do not replace the ball that you drew early back into the bag, the third time when you go to draw a ball from the bag, you know that there are only 8 balls, and among 8 balls, there are 3 blue balls. Therefore, the probability of getting a blue ball is 3 over 8, 37.5%. So that really helped to illustrate the difference between sampling with replacement and without the replacement. Now we have a very similar question to this one in the in-class activity concerning the calculations of probabilities. So we do not do this question here in the interest of saving time. Now let's move on to the relative frequency approach toward the determination of probability. This approach is to calculate the relative frequency of a particular outcome's occurrence. The percentage of times of an outcome occurs in the long run under the stable conditions is used as a probability of a particular event's occurrence. And this is calculated by using the number of times that a particular outcome occurs divided by the number of times all outcomes occurs in a sample. Now, since we mentioned that this percentage should reflect the long-term and stable conditions, that is what gives rise to this preference for large sample size, because when you have a large sample size, it is more likely reflects the long-term and stable conditions. For example, we know that toss a coin, you may get a head or get a tail, and get each size probability is 50%. But if you toss randomly 10 times, toss a coin 10 times, you may get exactly 5 heads, 5 tails. You may get 6 heads, 4 tails. So the probability of getting a head is 60%. But if you toss a coin 100 times, you may get 56 heads and 44 tails. And that makes the probability of getting a head 56%, compared with 60%, it's closer to 50%. And if you toss a coin 1,000 times, you may get the heads 497 times, and that bring the probability of getting a head 49.7%, very close to 50%. So with the increasing number of tauses, the sample size increases, and eventually, with a very large sample size, that then that the probability approaches the theoretical 50%. That will illustrate the large sample really reflect this long-term stable and expected results. Now, this is an example of using relative frequency to determine the probability. And this is what many insurance companies actually are doing. They got there to collect information concerning the traffic accident, and they calculate the probabilities of various outcomes of traffic accident. For example, from a particular sample of 567 people that involved in traffic events, so they find that 52% of them involved no accident, and 48% of them involved in accident. And this is a age group of 15 to 25. They use this percentage to get a sense of what is the likelihood, what is the probability of people of that age group were involved in a car accident. Then at a different age group, for example, 25 to 34, you have only 43% of people who are involved in the traffic accident. Then with rising age group, this relative frequency decreases. That really eventually gave rise to the practice that the older the drivers, the lower the the car insurance premium. So this kind of information comes from the real world sample, and after they collect the sample, they just calculate the relative frequency for various kind of outcome of a vehicle traffic accident. And you can also calculate that among those who involved in a traffic accident, what is the probability that involved injuries, and what is the probability that involve a death. And again, all these are examples of using relative frequency as a way to calculate probabilities. Actually, in the real world situation, you really have no way to determine the theoretical probabilities. And the only realistic way to determine the probability in the real world for different age groups is to go out there to collect data to calculate the probabilities. And because the traffic accident is a very complex event, that there are many factors that determine the traffic accident frequencies and the relative frequency. So there's no way to theoretically derive as any result. So you really have to collect the real world data to do the empirical calculation. Then we have a subjective probability. Subjective probability is also called a personal probability. This is to determine the likelihood of some event of happening by using personal experience, personal understanding of the events, and depending upon how well we know the kind of events, we may have a different probability estimations. Federal Reserve chairman, when they come to decide the monetary policy of the country to raise or decrease interest rate, they really have to, based upon their forecast projection of the future economy, but because different economies have different opinions about what's going to happen to the future economy, that's why there's a debate about whether they should increase or should decrease interest rate. If they decide to increase interest rate, how much to increase. So there's a lot of subjectivity here involved. Also, the personal experience, even political views involved here. So there's a lot of room to put the personal's input into the process. There's no objective way to determine the probability. So this is the third way to determine the probability. Basic characteristics of a probability. For a particular outcome of an experiment, probability is bound between 0 and 1. And you cannot have a probability that is negative. You cannot have a probability that is over 100%. It's bound between 0 and 100%, which is 1. Also, for an experiment that has different possible mutual exclusive outcomes, 1 through n, the probability for different outcomes will add up to 100%. For example, if you roll a die and you know that you could get one of the 6 possible outcomes, each outcome is about 16.7%. So the probability of getting 1 is 16.7%. The probability of getting 2 is 16.7%. And all these 6 numbers are mutually exclusive. You cannot get 1 at the same time get a 5. You cannot get that. There's no simultaneous result. You either get 1, either get 4, you don't get 2 together. Okay. So this is called exclusive, mutually exclusive outcomes. And for these kind of outcomes, they add up to 100%. Okay, expressing probabilities. This is one way to express probability. Formally, we use P to represent probabilities, using the statement within parentheses to represent the particular outcomes, and followed by the percentage number. We do not get into this part of the discussion right now, because we have a in-class activity specifically give you the opportunity to practice how to express probabilities in mathematical notations. So we're going to skip this part very quickly. Okay, let's just skip this part very quickly. You're going to see these questions in the in-class activities. Probability distribution. Probability distribution is the tabulate or use table or graph to show the events and their corresponding probabilities. Okay. For example, this is one way to see. This table is one way to show probability distribution using the form of a table, tabulation of probability distribution. In this context, we have so-called theoretical probability distribution. Here, probabilities are based upon logical reasoning rather than actual experience. You toss a coin, you know that the probability of getting a head is 50%, and probability of getting a tail is also 50%. And flip a coin 2 times, and the probability of getting 0 head is 25%. The probability getting 1 head is 50%, and the probability of getting 2 heads is 25%. We have shown this um, this probability calculation earlier. And these, you get this result not because you keep tossing coins, but because you use logic to derive at this result. So that's why it is called a theoretical probability distribution. Now we tabulate the theoretical probability distribution. Okay. An empirical probability distribution, and probabilities are relative frequencies established by experience. We have seen this example before. These are not the result of theoretical logical derivation, but the result of using the real-world data to calculate the probabilities of not involved in traffic accident, and if you involve in a traffic accident, what would be the probability of somebody got killed or get injured for different age groups. This is to use a table, tabulate probability distribution. These are different outcomes of the experiment. These are different relative frequency, and this table shows the probability distribution, the different outcomes and their corresponding probabilities. We can also use graph to show the probability distribution. Okay. Now here, the different colors of bars show different outcomes, and the height of a bar show the probabilities. We also have a discrete probability distribution. Here, for the random variable, the outcome are discrete variable. And here, you can really see why discrete variable. You can see murder, robberies, assault, so on and so forth. All discrete events. And for discrete variable, we can count the frequency of occurrence, and from frequency of occurrence, we calculate the relative frequency as probabilities. Okay. We can also use this graph to show the probability distribution for discrete variable. Now the flip a coin twice the number of heads, obviously is a discrete variable. This variable can only take outcomes such as 0, 1, and 2. You don't have 0.7, 1.5. You don't have those kind of numbers. So this is a discrete variable. So we obtain the probability distribution for discrete variable, and this is called a discrete probability distribution. And for discrete probability distribution is very similar for discrete variable bar charts. All these bars are not adjacent to each other because there's between 0 and 1 there's no any other numbers involved, so they had to be clearly separated. Now this is another example of discrete probability distribution. You have also different whole numbers 2, 3, 4, 5, 6, 7. Between 2 and 3, you don't have 2.7, 2.9. You don't have those values. So that form a discrete probability distribution. We have seen these examples earlier. We can also use a bar chart to show the discrete probability distribution.